Hi, in this lesson I will explain how to transfer data between a processing system and a programmable logic by using high-level synthesis for such devices like Zynq 1000 and Zynq Ultrascale Plus. So, before course introduction, I would like to explain why. Why basically we need to use high-level synthesis in order to transfer data, since Xilinx already offers bunch of different DMAs. So basically the answer is quite simple. All these IP cores, I would say, have two main drawbacks. First of all, it requires, of course, profound knowledge in order to work them. And another drawback, very also important, so it's really time consuming in order to learn how to work with them. It's significantly time consuming. And here I am not mentioning cases when, for example, this IP course needs to be up and running under Linux, when engineer needs not only to write, for example, user space driver, but also kernel model, and it could be quite overkilling. Or, for example, using, even though ready to use, like different kernel AXI DMA proxy kernel drivers, it's also for many engineers it can be quite overkilling and time consuming. And in this case, high-level synthesis looks quite good as alternative to all these IP cores. So go back to lesson structure. First of all, I will explain hardware design Vivada, where I have two IP cores, transmit and RX DMA. I will transfer data from DDR to TX DMA, then to RX and back, and afterwards I will compare send array and received array. So this hardware design I will use in Linux. So the second step is how to build and deploy a Linux by using Buildroot. And the third third step. It's three cases where I will run three different applications. So first, it's a standalone application for Cortex R5. So under Linux, I will work with remote processor, where I will run C standalone application. Second case, it's a Linux C application itself, and the third one, it's a Python application. So I will use Python environment in order to run the same test. So again, let's summarize. So all three test cases will run will do the same. Maybe difference that standalone will work with interrupt mode, so where it will accept interrupts from TX and the RX XDMA, and Linux C app and Python environment. And Python app will use polyt mode. And another feature, very important, that in all three test cases, I will use high-level synthesis DMA driver that usually come along with the IP cores. So by using these educational packages, following objectives can be achieved. So first of all, it's a hardware design. As explained, it's how to create these IP cores with different interface, how to connect them, and how to use them, set up and running, how to bring up in order to transfer data. Then, embedded Linux deployment with Buildroot. So here I'm not going to state that Buildroot is much better than other tools like PetaLinux, like Yocta. So each tool has own advantages, drawbacks, and so on. So I am using here Buildroot, and I find quite simple this tool quite simple in order to build and deploy Linux for Zynq devices. Yeah. Besides that, my embedded Linux will have some configuration for example, kernel or RTFS file system packages additional for device tree in order to meet all requirements to run all these three software test cases. And one example here, I will show how to work with FPGA manager. framework that allows to do configuration of programmable logic in device tree during runtime from Linux without rebooting one. So, OpenMP, Open Asymmetric Multiprocessing Framework. So it's an example, it's a test case number 1. So it's an example where I will run standalone C application in interrupt mode on Cortex R5 by using Linux. So from Linux, basically, quite good example. So next one, it's how to use basically a high-level synthesis driver. So again, the same driver can be used either for Linux, for Python, and for standalone. So, and I find this quite useful because in this case, there is no need to write driver from scratch. So driver will be auto-generated, and it's quite good basically. And the last one, it's Python. It's a Zynq, simplified wrapper interface generator. So this tool is used in order to create wrappers for low-level C sources and use them in Python environment. I find these tools quite remarkable, especially for team of engineers, where some engineers don't want to waste time in order to deep dive into low-level programming, and they are, for example, comfortable with Python, another is comfortable with C, and so basically Zynq generator allows to combine them together and allows to set work quite good and quite simple for all different cases. For my educational package, I create repository. Let's see what are the folders here. So first of all, yeah, so folders. Okay, so here are a set of different folders. Every folder possesses its own README file with explanation how to work with the folder. These folders are, so first of all, it's Buildroot with Buildroot sources to build and deploy Buildroot on the target. So doc, it's a folder with these TX slides. So high-level synthesis sources, and the 3 Linux and 3 software test cases. So besides that, here a Vivada hardware folder. So this folder consists of different sources in order to build Vivada hardware design and to create boot bin binary file to load Linux from, for example, micro SD or from flash memory. So first question, Vivada hardware design with AXI DMA IP cores. So this is a hardware design that I'm using in my Vivada. So here I can be seen to IP cores that is connected via AXI memory mapped interface to processing system. Also both interfaces have a AXI stream interface. They connected together via FIFO. And besides that, there is 2 AXI controls. So this is the AXI light interfaces that allows to communicate with the IP cores from processing system. Besides that, here I have interrupt connected to interrupt controller of the processor system. It's a 4-case standalone application for remote processor. Okay, so let's go further. Yeah, as I mentioned before, all sources can be found in the following. Accordingly, you need to go to some directories in order to find all the sources. For example, high-level synthesis source directory consists of hardware sources. It's a sources that's used by Vitis HLS in order to build both IP cores and software drivers. So basically they will be auto-generated, but I already copied them in the inter software folder here. So here code snippet from axidma.h. So I just insert this code snippet in order to explain interfaces that every IP core has. So basically here, first of all, it's interface for AXI. AXI, it's a master AXI memory map interface, stream interfaces in order to output or input data by using AXI stream interface. And besides that, there are two variables. So data that I would like to try to send from DDR and receive to the DDR back, it's a two-dimensional array. Two-dimensional array, and I just denoted it's like, for example, frame width. It's a number of lines and number of samples per line. So it's like video frame, again, number of lines and number of samples per line. So this is a register map for each IP core. So it's quite basic. So here can be found control in order to run, stop, and restart, for example, IP core. Also, there are 3 registers for interrupt. So another register, it's a register that is used in order to provide a pointer where to write or from where to read data, so pointer to each IP core, and 2 more registers for frame parameters, because every IP core should be aware how much data should be sent or how much data should be received. So, and the last picture that I would like to note here, it's memory map. So here I would like to pay attention, you pay attention on memory mapped interface. So each IP core has access to DDR, to full DDR memory, to full range. And besides that, for processing system, both IP cores, they are like a memory mapped device. Okay, let's see how to start working with repository. So in order to start with educational package, first step is to go to Vivada hardware folder. So here can be found make file and the readme with some explanation. Let's run make with the help target. And here can be seen a list of targets. So HLS, by using this target, Vitis HLS projects, basically 2 projects will be created for TX and RX days. Hardware, it's Vivada hardware project. Device tree, this target is used in order to generate device tree sources. FSBL, basically not only FSBL, it's a first step bootloader for Zynq Ultrascale Plus and power management unit. So both ILF file binary files will be created by using this target. Boot target is used in order to generate boot bin image for micro CD or, for example, flash memory. So first target that must be run, of course, it's hardware design. So why basically hardware design? Because for further steps, XCA or exported hardware design file should be created. So let's see. I already ran this because to build Vivada project takes quite long time, so I do this before preliminary. So and here in images folder already XA file is created. Here also I would like to mention that all targets in this folder should be run on system with Vitis and Vivada tool installed. So it means that, for example, I have here already Vivado, I have here Vitis, so and that's why actually I can work. Yeah. So again, since already XA file is created, let's build IP cores. So here I have already a folder with pre-built IP core sources. They are placed into IP cores. So let's see this. Let's go to IP cores, and here, for example, yeah, can be seen. So here I have two subfolders for RX and DX case, and here also can be found two zip archive. So when make with HLS target will be run, this zip archives will be recreated, and afterwards they should be unzipped in order to have all these sources. Okay, let's delete them and run Vitis HLS in order to create these zip archives. So remove AXI DMA RX export Zym AXI DMA TX also export Zym. Okay, let's see. Okay, nice. Yeah, we don't have them, so let's go one step upper and okay, and let's run make high level synthesis target. Okay, let's check if we have. Let's go back to IP cores folder and let's check. Yeah, so export zip file can be found here. Okay, so basically what I would like demonstrate also how to build, for example, FSBL. Since we have already here XA file, FSBL, and power management unit, IL file can be built. Okay, let's run make FSBL. Let's check images file again. Images folder, sorry. So yeah, here can be seen that FSBL was generated, power management unit, also bitstream was added. So yeah, and basically the last target that I would like to demonstrate, it's device tree. So for doing this, device tree target should be run. Okay, ready. Let's take a look. We have to go to build folder. Here, device tree folder, device tree folder, and output. Yeah, we need to go to output folder, cd output. Let's see. Yeah, and here can be seen that all device tree files for this hardware design were generated successfully. So the next step is to build and deploy Linux on the target by using Buildroot. First of all, I would like to mention what is the system software and what kind of artifacts I needed in order to up and run Linux on Zynq 7000 and Zynq Ultrascale Plus. So here I'm using two different colors. So a green one I'm using for just Buildroot, and the yellow one is used for Vitis for Xilinx SDK tools. So it means that by using Buildroot, kernel can be generated, rootfs file system, device tree, binary file, second bootloader, and untrusted firmware for Zynq Ultrascale Plus. By using Xilinx tools, Vitis, for example, so it's a first step bootloader, bitstream, device tree also, because device tree configuration depends on memory, map devices, and PL part, for example, and PMU firmware for Zynq Ultrascale Plus. So why basically Xilinx SDK tools here? Because all these tools, they are platform dependent, so they depends very tight on Vivada hardware design. So that's why actually Xilinx SDK tools should be used. So other system software or other artifacts can be generated by using Buildroot. So as I mentioned before, I have here a Buildroot folder where I have all necessary package in order to all necessary package and kernel configuration, device tree, in order to meet all requirements to run software, all three software tests on a target. So some features that basically I would like to note that I have for my Buildroot out of tree configuration. So first of all, it's a Linux system software itself. So with Buildroot, I am able to generate second bootloader, untrusted firmware, kernel, device tree, and RTFS file system, device overlay support, as I mentioned before. So this feature is quite important in order to do configuration of programmable logic part during runtime. So a Linux memory reserve, since we are working with DMA, DMA requires some physical memory that cannot be touched by Linux. So in this case, memory should be reserved, of course. FPGA configuration manager framework. So this framework is tied to device over tree also support. So I'm used to remote update, remote boot of programmable logic part, and libmetal and OpenIMP framework. So this framework I'm using in order to run application on remote target. For example, in my case, it's a Cortex R5 processor. And finally, it's a simple wrapper interface generator Zynq. So basically, my Buildroot build is is host. It's a host for hosted this Zynq. So and I'm using this Zynq as on this host in order to create a Python wrapper and in order to use all C low-level applications in Python environment. Okay, so let's go to the folder build. So Buildroot, sorry. Here make file in order to build and get all system software. So basically just make command should be run. I already did this because it's quite time consuming. So let's see what's here. So in build folder, there are two subfolders. Buildroot with repository of Buildroot itself, and target is what was built basically. So let's go to this target because it's already built, and here are the folders that I'm using in order to compile my applications. So also here cross compiler can be found. Let's go to the folder images and see what kind of artifacts already is generated by using Buildroot. So here can be found it's a kernel itself, untrusted firmware, RTFS file system, binary file, it's device tree, and second bootloader. So all these artifacts can be used in order to deploy and up and boot Linux on the target. Let's generate boot bin file for a Zynq Ultrascale Plus. To do this, we need to go back to this Vivada hardware folder. And since we have ARM trusted firmware and second bootloader, we can build boot bin file. So first of all, let's see what we have in images. So yeah, here we have no boot bin file. Then just like run make boot and okay, again. Okay, nice. So bootbin file is created, and this bootbin file can be used in order to load Linux on the target. So basically, bootbin file here comprises the following binaries. So first of all, it's a first step bootloader. It's a bitstream. It's ARM trusted firmware and PMU firmware and Ubuntu. So there is no rootfs file system, no device tree, and no kernel. So this file should be used along with image ITB. So image ITB, this is a binary file that comprises image itself, rootfs file system, and device tree. So again, in order to run Linux on the target, two files are required. So first it's a bootbin, and second one it's an image ITB in this educational package, of course. Okay, so let's run three software cases. So first of all, I would like, before I will start, I would like to mention what is drivers for high-level synthesis. So this is a bench, this is a set of drivers. It's a common drivers, and the description of the drivers can be found in the Vitis HLS documentation. So here I would like just to pay attention that some drivers, they are shared between either Linux or standalone application or bare metal application. Some drivers, they can be used only for standalone application, and some drivers can be used for only for Linux application. So basically, that's all information about drivers from high-level synthesis. Quite simple. So you can take this driver and use this either on Linux or as standalone. Okay, so first of all, let's start with a standalone application and OpenMP framework. So what I will do, so here, since I have Linux running on Cortex A53 in my Zynq Ultrascale plus target, so, and I have remote processor, it's a Cortex R5. I will use Linux in order to load executable ILF file on the Cortex R5 and execute it. So quite simple. Okay, let's start. In order to do this, I have to go to this non-OS directory. So here can be found sources. So basically, this is the sources I would like. I would like to show this. What is the sources? Quite simple sources. Here I have array parameters. I specify 16 lines, and each line consists of 1024 samples. Also here I have interrupt controller libraries, since I would like to use interrupt mode, and handlers. It's interrupt handlers for RX and TX. Here I have also function compare arrays. This function will be across all three test cases. So this function simply compares sent and received arrays. So basically that's all what I would like to have. Okay, how to work? So in order to run, let's check make help. So here are three targets. For first time, I need just to run create app, and then I can, if I do some changes in my C file, I need to call just build up. That's all. Let's start with make create app. Create app. Okay. Yeah, first time it takes. Yeah. So while it's building, let's connect to a target. I have my target connected to my Linux, and I will connect by using COM port and Ethernet I will use in order to transfer data from my host to the target. Okay, first of all, let's connect USB1. Okay, this is a COM port 8. Okay, I will rerun Linux, reset my board again. Okay, my Linux is booting. Okay, let's go back to the Linux just to see how things are going with application. Okay, it's still building. And here I have a Linux. Okay, I can log in. By default, it's root. First of all, let's check if config. So here I have my IP address, and let's see if I can access the target from my host. Okay, let's wait for a while until the standalone application will be built, and afterwards we need to copy binary file on the target. Also, I would like to mention here that I'm using for OpenMP, I am using not only C file itself, um, so file links script file also can be found here. So, and where I have defined what kind of section memory stack heap where I would like to place in the memory. So, and yeah, so first of all, this is a IL file. Let's check. It's a link script that I mentioned. So basically, in order to build this project, both files I use it. It's a C file and link script. Okay, so the next step, I would like, first of all, I would like to program PL part. In order to do this, I need to copy my bitstream. I have to go to images and this is bitstream. Let's copy this onto target 3. I will copy this directly into root directory. Okay, let's check. It's here. Then I will call FPGA configuration manager in order to program bitstream file. Okay, successfully loaded. And the next I have to go to the directory lib firmware. So here I have nothing right now, and afterwards I need to copy to this directory just 2 files. This is my ILF executable file and the shell script that I'm using in order to execute file on remote processing system. Let's copy them both, SCP R5 ILF, and then I have copy run application. I will copy this again on my target. And the folder that I will need, it's lib folder firmware. Okay, let's copy. Let's check. Okay, so here we are. In order to run, first of all, I need to load application, load, and then I can start this. Run with start. Let's see. Okay, so what I have here. So first of all, so here I'm transferring a frame with 16 lines and 1024 samples per line. So setup interrupt system was initialized successfully. Then transfer, for me, transfer took 212 microseconds. So after I receive array, they were compared and they are equal. And here I print out 5 first and 5 last elements, 5 first and 5 last elements of each array in order to see that they are equal. Since I am using pseudo generator in order to create this array, and besides that, a RX done flag that was set in the RX handler, was set correctly to 1 from 0. Okay, let's stop and run again, just to make sure that my array content was changed. So yeah, it's a little bit different, so it's quite different, and but it's still the same. So array are equal, RX done, and the transfer took, yeah, approximately the same. Okay, so let's stop and let's change parameters of the frame. So for doing this, I will need to go back to the sources and I will use here 1024. For example, 1024 by 1024. So in order to create, I need to run again make, but not create, but build up. Let's see, build, in order to rebuild, build app. Let's run it. Okay, so finished building projects. Here can be found this ILF file, and all I need is to copy again to the target. I don't need to load one more time, so all I need is just to start. Okay, done. So it took it took longer. Again, so here we had 212 microseconds, but here it's 13,400 microseconds. So arrays are equal, so Rx done. We got this flag, and we can see that the last and the first and the last 5 elements of each array are also equal. Okay, let's stop and let's repeat this again. Yeah, and in the beginning here, I printed out how much data I'm transferring. So 1000 by 1000. So. Okay, nice. Let's stop. Second test case. It's a Linux application. So first of all, I would like to explain how I'm using high-level synthesis drivers in Linux. In order to have access to memory map device, memory mapped in physical space, in PL part, I am using user input output framework. So this framework allows me to map all devices that actually I would like to have in user space. They are mapped into from hardware physical address space into user virtual memory space via kernel virtual memory space. So, and by using some interface there are some functions, like for example memory map function, L control function, read write function. So basically this framework allows to work not only in polite mode but also in interrupt mode, but I would say that it's not like a pure interrupt compared to standalone, for example, but it's mostly like polite mode but based on state of interrupt controllers. So that basically that's all. But again, for user space it will be completely the same, polite mode. So that's why basically here I'm using polite mode. The second point that I would like to mention here, of course, it's a question how to bring all these devices into input-output in user input-output framework. So in order to do this, some device tree modifications are required. So and afterwards, devices can be recognized as IP cores can be recognized as user input output devices in device tree. Okay, let's see how it works. Basically, first of all, what we need to go to this Linux C directory. So it's quite simple. So here I have just the 3 files, readme, makefile, and user app itself. So in order to build, just run a make. Okay, and by the way, cross compiler is used from Buildroot out of 3, so Buildroot should be built, of course. So okay, here I have user app, and let's copy this user app just directly on the target in my root directory, where I have already my bitstream. Okay, let's copy, go here. Okay, yeah. Yeah, sorry. Okay, this one, I guess maybe. Yeah, here I have user app. But before I will run user app, of course, I have to configure device tree by loading device tree overlay and again bitstream. So in order to do this, I will use FPGA configuration manager. So I will use the same bitstream, and for device tree overlay I already prepared this device tree overlay by using Buildroot, and I just put it into user overlays linux.tbo file. Okay, so here is a file. Let's run it. Yeah, so but yeah, sorry, before we will run, okay, yeah, let's run. So okay, it's loaded. Let's check basically for doing this prots device device. Sorry, yes, prots device 3. AXI golf. Sorry for not here. We need to go. I guess maybe. Sorry, not here, but here. Prots device 3. No, here, not here. We need to go to device. Let's see device first. So here I can see 6 EU devices. So basically, let's yeah. If I remove by using again FPGA manager framework, if I remove my overlay, let's check again. I will have only, instead of 6, I will have only 4. So it means that 2 devices. So where so here it means that the 2 devices were deleted as well. So okay, let's check device stream. So yeah, it's here pros device 3 AXI. This maybe I need a little bit long. Yeah. So here we have no memory map devices from PL part, but again, if I program it, let's check again. Yeah, and here it can be seen that I have 2 more devices, so it's my HLS IP cores. Okay, so we are ready to execute binary file from Linux C application. So let's start. Yeah, and no, because we need to specify parameters of array we would like to send. Let's use the same parameters that was used for standalone application, 1016 first 16 by 1024. Okay, so it's done. So let's read log. So transfer took approximately the same time. In case of standalone application, it was 212 microseconds. Here it's 237. Arrays are equal, and yeah, first and last 5 elements of the array. Okay, let's run again just to check that content of RX and buff and the X buffer are changed here. So yeah, it's another. And let's change frame parameters. The frame parameters here will be 1024 by 1024 as we did for standalone application. Let's check. And arrays are equal, and transfer time is again the same as it was for standalone application. So let's run it one more time. Okay, nice, it works. Okay, and the last test case that I would like to explain in the lesson here, it's a Zynq or Python environment. First of all, I need to go, let's make clean here, and let's go to another folder where the sources are placed. So it's Py folder. Okay, here we are. Okay, let's go to the X. So what is a Zynq? So basically for Zynq, I will use drivers that come along with HLS IP cores. I will create Python wrappers for these drivers in order to use these drivers directly in my Python script. The Python script does basically the same as the standalone application on Linux C application. So Zynq will take these C sources, will take AXI DMA interface file, and then will convert all these sources into 2 files that basically are required in order to run C low-level application in Python environment. This is the files. They are AXI DMA Py module and shared library. So afterwards, I have to copy this Py module shared in the shared library with user app on the target, and then can execute. So first of all, let's take a look on content of this user app. Py script, basically it's, let me open it. Okay, yeah, here we are. So here I am import this AXI DMA Pi model, and afterwards, so I call just all these files, all these drivers by using Python environment. Okay, let's do and let's check how it works like. Okay, here we are. So just we need to make. It takes time. Okay, ready. Let's check. Nice. So here I have AXI DMA shared library. This is my model, and this is my application that I would like to. Yeah. Also, I failed to mention. So basically, since this Zynq application exploits the same drivers, of course, for Linux we will need this UIO user input output framework. So I will not load again bitstream and device tree, since we already have all these devices. So I will just execute this Python script. Okay, let's copy this Python script on the target. Okay, I will use user app Pi. Then we will need shared library, and also we will need AXI DMA Pi. Okay, ready. Let me just check what we have here. Here I have system grip. Okay, nice. Okay, let's run. Okay, and let's check here. Yeah, we have on the target. Let's just execute Python user app Pi. Yeah, and I need to specify arguments. I will set frame size the same as we did for previous both cases. Okay, let's run and check. Oh, okay. So let's read. So first of all, this RX and TX buffer, they are NumPy arrays. So this is the first 5 and the last 5 elements of each buffer. Arrays are equal, and time for transfer is yeah, it's faster, or it's the same, or it's so standalone. So plus minus 5 microseconds basically. Let's call it again just to check that it works. And array content was changed. Yeah, so it can be seen from here. So, and it's a little bit faster in this case. And let's change frame parameters. 1024. Okay, let's run it. Yeah, so the time was like the same for both previous two applications. So let's run again. Okay, arrays are equal, first last 5 elements, and let's execute. Since we have already user input output devices here, so we can just execute again C application, just to see that time is quite similar what we had during run user app Pi script. Okay, so here basically I would like to stop. So I hope really you enjoy this video. I think this educational package is quite it's extremely useful for all kind of engineers who are working with not only basically Zynq 7000, Zynq Ultrascale Plus. Some stuff can be used also for another kind of Linux, another kind of system on chips, and so on. So please, if you have any questions, ask. If you would like to get this educational package, I would like to remind that it's a paid part, it's commercial part of my project. So please just give me your request and I will explain how to get. So just one short notice about, again, folders here. I would like just to notice that all folders will be found in this repository. So I just did demonstrate how to work with the repository. So please feel free to ask questions, to request the package. Yeah, I hope you will enjoy it. And yeah, I hope that level of engineers can be raised just by using this video. Bye.